Good afternoon once again, fellow scholars. It is I, Chris Crowe, and today we are going to be going over another PowerPoint presentation. This time it is Lesson 3 over Chapters 3 and 4, which I believe is integers and factorizations. So, without further ado, let us get on with the lesson. Number 3, yes, presentation 3, chapter 4, number 3, chapter 5, integers. My apologies. So moving forward, we're going to see an example of a table. We'll be using this as a form of graph for our first question, which deals with divisibility rules. Now, what are divisibility rules? Well, the simplest I can explain are they're the rules that tell us what a number is divisible by when dealing with other numbers. So, for example, at the top of the graph, we see numbers 684, we see 2064, we see 51,051, 644,490, 2,676,740, and we see 50,250,528. And we've also been given an example for number 684. Now, if you look at the bottom left corner of the screen, you will see that I've set up divisibility rules for numbers 2, 3, 4, and 5. We'll move on to 6, 7, 8, 9, 10, and 11 in a moment. For now, we can see that the rule for number 2, if the number ends in an even digit, the whole number is divisible by 2. And if we're looking up at 684, the example that's been given to us, we can see that yes, the number ends in an even digit, therefore it is divisible by 2. Now, with that in mind, we're going to move forward with the remaining numbers that are hidden. So, since 2064, 644,490, 2,676,740, as well as 50,250,528 all end in even numbers, they will all be divisible by 2, whereas 51,051 will not be because it does not end in an even digit. Now you might be asking, well, why are 644,490 and 2,676,740 divisible by 2? They end in zeros. Well, that's because zeros are also divisible by 2. Zeros are divisible by everything. So, the rule is a bit strange when the zero part is left out, but it follows that rule for 2. Any number that ends in the digit 2 an even digit or 0 will be divisible by 2. Now, going to the next rule, we see the divisibility rule of 3. If the sum of the digits added together is divisible by 3, the whole number is divisible. So what you'll want to do for these numbers is to add the digits of the numbers together. So 6 plus 8 plus 4, 2 plus 0 plus 6 plus 4, 5 plus 1 plus 0 plus 5 plus 1, and so on and so forth until you receive your answers. And once you have the sum total of the addition, if that total is divisible by the number 3, then the original number is divisible by 3. As you can see here, most of these numbers, besides 2,676,740, is divisible by 3, because their sum total amounts are divisible by 3. Moving on to the divisibility of 4 rule, we see if the final 2 digits form a number that is divisible by 4, the whole number is divisible by 4. So, as it says, if the final 2 digits of a number form a number that is divisible by 4, then the original number is also divisible by 4. So, for example, in 684, the final 2 digits of the number are 84. In the next one, it's 64, 51, 90, 40, and 28 respectively. Now going through those different numbers, you'll check which ones are divisible by 4, and you will have your divisibility rule. So everything is divisible by 4 except for our third and fourth example numbers. Now the final rule for this slide is the divisibility of 5 rule, which states if the number ends in either a 0 or a 5, the whole number is divisible. Now that's probably one of, if not the most simple rule that we've encountered so far. Going through the different example numbers, it's plain to see. Looking at the final digit, the one at the very right, in case you weren't already aware, if the number is a 5 or a 0, then the entire number is divisible by 5. If it is anything but, it doesn't fly. So going through the example numbers, we see that the only numbers that are divisible by 5 are 644,490 and 2,676,740 because they both end in zeros. Now, moving on to this slide, we have 6, 7, 8, 9, 10, and 11, as well as the same example numbers we were using for the previous slide. And we will go over their division rules as well, starting with 6 and ending on 11. So, starting with 6, the rule is, if the number is divisible by both 2 and 3, it is divisible by 6. So this divisibility rule actually depends on 2 other divisibility rules. And if you remember which numbers were divisible by which in the previous slide, you will know which ones are divisible by 6. No major math required if you've already done divisibility by 2 and 3. So, as we remember, 51,051 is the only number that is not divisible by 2 and 3, so it is not divisible by 6. Now, moving on to the divisibility of 7 rule, we take the last digit of the number, we double it, and then we subtract that result from the rest of the number. If the final sum total is divisible by 7, then the original number will divide as well. Now that may sound complicated, but I promise you it's not. It simply means you're going to take the final digit of the number, you'll double it, so you'll multiply it by 2, you'll subtract that number from the rest of the digits, so in the case of 684, you'll take 4, you'll double it, and then you'll subtract that number from 68. And whatever that final number is, if it is divisible by 7, then the original number, 684, is divisible by 7. And as you see here, we are given our answers, being our third and fourth example numbers are the only ones that will divide by 7. Moving on to number 8, the divisibility rule follows a similar one that we've seen before. For divisibility of 8, if the last 3 digits of the number is divisible by 8, the whole number will divide by 8. Now, for certain numbers, such as 684, there are only 3 digits, so it's as simple as grabbing a calculator or putting down on pen and paper 684 divided by 8. For the larger numbers, such as 50,250,528, you're going to take the final 3 digits of the number, in this case 528. You'll divide that number by 8, and if it's divisible, the entire number will divide by 8. And as you can see, we have a bit of a split between yes and no, although no seems to win out in the end. Now, the divisibility of 9 rule actually follows the same concept as the divisibility of 3 rule. For 9, you'll add all of the digits, and if the sum divides by 9, the original number will divide as well. So, almost exactly like number 3. You'll take all of the numbers, you'll add their digits together, and if that sum total divides by 9, then you have your divisibility of 9. Now, the divisibility of 10 rule is exactly as the divisibility of 5. If the final digit is a 0, it is divisible by 10, as counting by tens will almost always, if not always, end in a 0. So, looking at our example numbers, we see which ones end in a 0 and which ones do not. Therefore, we know which ones will divide by 10. Now, the final divisibility rule is divisibility of 11, which is by far probably the most, if not the second most, complex sounding one. But, as I said with number 7, it is not difficult. So, for divisibility of 11, you will subtract and then add the digits in an alternating left to right pattern. If the result is 0 or 11, it's divisible. Again, just like 7, it sounds complicated, but it's far simpler in practice. What you will do is you'll take the digits, and as it says, you will add them and subtract them in alternating patterns. So, for example, 2064, you will separate the 2 and the 6 from the 4 and 0. You will add those digits together, and if the result is an 11 or a 0, it's divisible. Or subtract, depending on whichever one comes first. And if we're following the graph, we will see that there are only 3 examples that divide by 11. Now, moving on to our next question. This is by far what I would say the most simple concept once you've figured it out. It starts out rather confusing and complex if you've never encountered it before. I'm of course referring to the method of counting out nines. Now we see here 416 plus 7,490 plus 69,844. Now we see it equals 112,790. Well, you might be thinking, isn't that our answer? Is it? We can check by using the counting out nines method. So first, we're going to add all of the numbers together, which is the simplest way to discover whether that answer is true or false. So, adding our numbers together, we can see a 0, so far we're on the right track. However, we are immediately given a 5 as our second digit, which is not matching up with the given answer. So, continuing on through the addition process, we see that our final answer is nothing like the one given to us. The correct answer is 77,750. Now that is far pulled from the original 112,000 answer. So, what do we go from here? Well, bringing this to a separate box, we're going to take our actual addition answer, and we're going to divide it by 9, hence the counting out nines. And 77,750 divided by 9 yields a number with a remainder of 8. Now the actual number is inconsequential because the remainder is actually what we're most concerned with as far as the counting out nines method is concerned. Jot down the actual answer if you feel the need, but the remainder is what we need to pay most attention to. So now, going over to the right side, we're going to take all of the individual numbers and we'll divide those by 9. And they'll all yield their own answers with their own remainders. 69,844 divided by 9 will give us 4. 7,490 divided by 9 will give us 2. And finally, 416 divided by 9 will give us 2. So then we're going to add those numbers together, which will give us 8. So then we will take the 8, we will divide that by 9, and the answer will be whatever the number is with a remainder of 8. So, because we've tested this by counting out nines, we can see that 112,790 divided by 9 will yield a remainder of 2, which means it is not only the incorrect answer because of the standard addition, but also because the remainder number does not match up. Therefore, our actual answer is 77,750. Now, let's go on to our next counting out nines example. we have 8,550 plus 6,888 plus 2,525 plus 6,029. Now, if you were paying attention to the previous slide, we're going to use the counting out nines method the same as before. Now, the given answer is 23,892. Now, that may be the correct answer, or it may not be. Following the same pattern, we're going to add the numbers together, and we are going to be yielded the answer looking pretty close, but the digits are starting to not match up. We are given 23,992, so just 100 too short of our actual answer. So, following the same pattern, we're going to bring down 23,992. We're going to divide it by 9, which gives us a remainder of 7 after the actual answer, whatever it may be. So, going across, we will divide each individual number by 9 once again, which will give us 0, 3, 8, and 5 respectively. Once again, we're going to add all of these remainder numbers together, which gives us 16. Bringing down again, we're going to divide 16 by 9, which gives us whatever answer it is, with the remainder of 7. And going up to check 23,892 divided by 9, we see the remainder is 6. Close, but no cigar. So, counting out nines yields us the correct answer of 23,992. Our next example is throwing you for a loop. Or is it? 78,362 subtracting 3,674. Now you might be starting to get a bit worried because it's no longer addition, but counting out nines will follow the same pattern as before with a slight modification. So, continuing onward, we are given the answer 74,678. Now, if we've been paying attention to the last two, you understand that we need to question that answer. So moving forward, we're going to subtract these two numbers instead of adding them because we're subtracting, which will give us the answer 74,688, not 78. So again, close, but no cigar. And once again, we're going to bring down 74,688. We're going to divide the number by 9, which yields whatever number answer it may be, with the remainder of 6. Once again, bringing the original over, we're going to divide both of the beginning numbers by 9, which yields 8 and 2 respectively. And we'll once again subtract these two numbers, which gives us the answer 6. Finally, we're going to divide 6 by 9, which gives us the remainder of 6 we're looking for. And once again, we're going to test the given answer at the very beginning, which gives us a remainder of 5, which tells us it is not the correct answer. Instead, we are left with 74,000, I apologize, that's not supposed to be there, but the correct answer is 74,688, not the 23,000. So, moving to our final example, we have 337 multiplied by 620. Once again, they're pulling something different, they're trying to throw you for a loop, they're trying to scare you. Don't let them. We're going to follow the same counting out nines method that we've been using, with, again, a slight modification. Now the given answer is 209,940. Now once again, we have to question whether that is correct. It may be close, but it's not correct, as far as we are aware. Moving forward, we're going to multiply these two answers, which gives us 208,940. Once again, we're going to take that answer, we're going to divide it by 9, which will yield an answer number with a remainder of 5. Bringing over the two original numbers, we're going to divide them by 9, which will yield us the answers 4 and 8 respectively. Multiplying those together, we are given the product of 32. And bringing down that sum total, we get 32 divided by 9, which yields whatever answer it may be, with a remainder of 5. Now for the final time, we're going to test the original given number divided by 9, which yields a remainder of 6. Once again, the given number answer is not correct. Instead, our final product answer is 208,940. Just remember, whenever using the counting out method, counting nines method, the remainders match, you've most likely got your correct answer. If the remainders do not match, then there may have been a problem with your calculations and you need to go back and check. I know I made more than a few while doing these. Now, looking at our third question, you're going to see some colored blocks popping up. Colored blocks are always fun. And you can see that they're all different lengths, ranging from the smallest to the largest. These are at lengths of 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We'll call them units for now. And the first part of this question is what blocks can make up the 9 block? So if we see here, the 9 block is the blue, and what we need to figure out is what colored blocks will fit over 9. Now you might be thinking of several different combinations, and you wouldn't be wrong, but that's not what we're asking. It's asking what color blocks will cover the 9. Now in this, you're going to have to think of multiples. So in this case, we have the 9, which will cover itself, like all numbers will. And then we also have the 3 color block, the light green you see in the top left, which represents number 3. And like 3 times 3, they'll cover the 9 block, which equals 9. And then we have the 1 blocks, which 1 times 9 will equal 9. Now, moving on, we're going to go to number B, letter B. And this one is asking what blocks will cover the 6, the dark green at the very bottom right. Now, again, thinking in terms of multiples, we're going to go through the different numbers up until we reach 6. So obviously 6 will cover itself. And then we also have the 1 blocks, see, 6 of them will cover. And then we have the 2 blocks, and see, 3 of them will cover the 6. 2 times 3 is 6. We have the 3 blocks, and see, only 2 of those will cover up 6, as 3 times 2 is 6. And finally, as I said before, we have 6 itself. Now, moving on from B, we're going to encounter letter C, which is actually going to ask, what is the greatest common divisor of 9 and 6? Now, what is the greatest common divisor? Well, the greatest common divisor, put in simple terms, is the largest number that can divide by both 9 and 6. So, going through the different numbers, you're going to test them. You're going to divide them and see if they divide by 9 and 6. Now, they may do so, but you have to continue to go upwards until the numbers stop, until they no longer divide by both 9 and 6. Once you've found that number, the one that finally divides them both, you'll find it to be the largest number. So in this case, we are going to go through these different numbers. Now we see that they do divide by 9 and 6. 1 and 2 will divide by 9 and 6, but they're not exactly the largest numbers we can think of. Now 3 can do so, and we're getting kind of close. We know 4 and 5 don't. 6 will divide by itself, but it doesn't divide by 9. 7 doesn't divide by either. 8 won't divide by either. 9 will divide by itself, but it's too large for 6, so that rules it out. 10 won't divide by either of them. So our only number left is 3. 3 is the greatest common divisor. It is the largest number that can divide into both 9 and 6 evenly. All of the others are either non-divisible, or they're too large, or they won't divide by one or the other. So 3 will be our final answer. Now, moving on to our next part of this question, we're going to combine the 10 and the 8 block. Now, this forms what we call a train. And this train, instead of being 10 or 8, is going to be 18, using simple addition. And now the question is naming all of the blocks that will cover this 18 train. So again, we're going to think in terms of multiples. And if you've been paying attention, we'll go through descending order. So here we see 2 9 blocks covering up the 18 train, because 9 times 2 is 18. Moving on, we see 3 6 blocks, the 3 dark greens, and 6 times 3 is 18. Moving forward, we have the 6 3 blocks, we have the 9 2 blocks, and finally we have the full 18 blocks for the ones, because thinking in multiples, all of these numbers times something else will equal 18. Now, moving on to our final piece of number 3, you see the 18 block now on its own, and the question is asking, create all of the trains or blocks that will cover 18. Well, we just covered the different blocks the different rods that will cover 18 on their own or with others. Now, trains, if you remember what I was talking about, 10 and 8 put together is a train. So remembering that, we're going to think of all the different trains, all the different combinations of rods that can cover or equal 18. So going down, we see, obviously, 10 and 8. And then we're going down to the 10, the 7, and the 1. Now in this, we're thinking of terms of addition instead of multiplication, because trains are simply combining themselves. Here we see the 10, the 6, and the 2. Here we see the 10, the 5, and the 3. The 10, the 4, and the 4. And that would be it. Those are all the different trains that can cover 18 as a whole. Now moving on to our next question, we're going to be discussing the And finally, it's going to ask us how can we use these blocks to display greatest common divisor for younger students like yourselves. So, as I explained earlier, greatest common divisor is simply the largest number that can divide by two numbers evenly. And you see here I've got R equals S, or R equals 9 and S equals 6. And those are simply to represent the verbal explanation. So the greatest common divisor is simply the largest number that can divide into numbers R and S evenly, or in rod terms, the greatest number that can measure the largest rod between the two. So in this case, the largest number that can measure the largest rod is 3. Now moving on to our next question, we see here an example graph and then our actual problem graph. Now, like before, we're using a table to represent a square graph. So here in the example, we see a jumble of numbers. You might not even be sure what they represent, how they're related, and so on and so forth. Well, don't fret, because I'm going to explain. Similar to how GCD functions, LCM is the least common multiple. And that is simply the least common multiple, the number that can multiply by all of them, but in reverse. So it's the least common, so probably the smallest number. Now, looking at our actual question table, we see the numbers 48, 25, and 65. Now, the point of this particular LCM method using the table is we're going to find the least common multiple of all three of these numbers, rather than just one at a time. So going down the very leftmost side of the table, we're going to pick apart different numbers that are divisible by our given numbers. And as we go down the graph, we'll be figuring out our prime factorization form numbers. Now, prime factorization form is the numbers within prime factorization. And if you're wondering what prime factorization is, it is similar to how you will use a tree diagram. You're going to take a number and you're going to break it down to all of its multiples. And you'll continue to break down, creating branches of the tree until the numbers cannot be broken down anymore. And then you'll take all of those prime numbers and then you have your prime factorization. So moving forward, we can see 48, 25, and 65. Now you'll want to start off with the number 2 and then slowly increase or stay the same depending on divisibility. So starting off with 2, since 2 is divisible by 48, we're going to eliminate the next 3 boxes below 48, 25, and 65. So 2 divided by 48 is 24. Now 2 does not divide by 25 or 65, so what do? Well, we simply bring them down. They don't change until they encounter a number that they can divide by. So once again, we're going to repeat that method, and since 2 is once again divisible by the first number, we'll do 2 again. So 2 divided by 24 is 12, and once again, 2 won't divide by 25 or 65. Therefore, they're going to remain the same. And we'll continue this pattern, so 2 divided by 12 is 6, once again bringing down 25 and 65. 2 is divisible by 6, so our next number will be 3. Once again, 25 and 65 remain the same. And now we reach a point where 3, as you may have learned previously, is a prime number. And what a prime number is, it is a number that only has 2 divisible factors, 1 and itself. To get 3, you can only either divide 3 by itself or vice versa. So we can no longer use 2, as it does not divide by 3, nor does it divide by 25 and 65. And both of those numbers can be broken down further. So what we're going to do is we're going to use 5. Now why 5? Why not 3? Well, as I said before, 3 is a prime number. It can't be broken down anymore unless you want to break it down into a 1. But you'll be following that pattern for quite a long time, and we're trying to move along. So we're going to use 5, because 5 is divisible by both 25 and 65. So breaking down, 3 remains the same, 25 becomes 5, and you'll know 5 is also a prime number. Now 5 divided by 65 is 13, and if you're paying attention, 13 is also a prime number because it can only have the 2 factors, 1 and itself. So now what we're going to do is we're going to count up all of the prime factorization numbers. So all of the numbers at the top, at the farthest left column, and all of the numbers in the bottom row. And once we've counted them all, we see 2 times 3 times 5 times 13. And as I said before, prime factorization will typically require you to do exponents. Now exponents are these top numbers. And if you're wondering what they are, what they represent, you simply need to pay attention to the graph or the table. You'll see that there are 4 2's in the prime factorization column. So 2 to the 4th power, 2 times 2 times 2 times 2. And that goes for all of the numbers. There's only 1 3, there are 2 5's, and there's 1 13. And since those are the prime factorization numbers, this right here is our prime factorization expression. And we're going to follow that same pattern for this example. Now, once again, the first number we're going to use, because it's the divisible by 40, is 2. Now, let's say 40 were a number such as 39, where 2 is not divisible. What you'll simply do is continue to go up in numbers until you find a number that is divisible by 39. That's assuming that none of the other numbers in the row are divisible by 2. You'll go through the entire row, and if none of the numbers are divisible by your current prime example number, you'll simply go up until you find a divisible. So 2 divided by 40 is going to be 20. 2 divided by 12 will be 6. 2 divided by 44 is 22. And then 2 divided by 363, well, that doesn't divide. So as I said before, it's going to be brought down. And repeating this pattern, we're going to continue on using 2 until it is no longer usable. So then we have 10, 3, 11, and 363 remains the same for now. We'll use 2 again, which breaks down to 5, 3, 11, 363. Now 311 and 363 remain the same because they don't divide by 2, either because they're non-divisible or because they're already prime, such as 311, such as 3 and 11, as well as 5. Now once again, 2 is no longer usable, so we're going to increase to 3. So then 5 remains the same, 3 turns into 1, 11 remains the same, and 363 will now break down to 121. Now you have to make sure that you completely factor everything until you know it is no longer necessary. The 3 could have remained, but it also had to bring down the 363, otherwise it would remain a non-prime number. So we're going to use 11 as our final prime number use, as it is the only one that will go into 121. So 5 and 1 will remain the same, 11 will become 1, and 121 will become 11. Now if you're wondering why we're going to stop there, why won't we break down 11 further? Because it doesn't need to be brought down further. 11 is a prime number. Its only factors are 1 and itself. The only reason we brought down the 11 in the second to last row is because it was necessary to bring down the 121. So we have our prime numbers, 1 times 2 times 3 times 5 times 11. And if you're counting up all of the numbers, we're going to have 1 to the second, 2 to the third, 3 to the first, 5 to the first, and 11 to the second. And that is our final answer, our prime factorization expression. Now we're going to look at our final example for this. We have 250, 28, 44, and 10. So once again, even though the first number is an exceptionally high one, we're going to look at the first number that is divisible by it. So in this case, 2. So divided by 250, we have 125, we have 14, we have 22, and we have 5. And going down further, we're going to use 2 again, which divided by 125 remains 125 as it won't divide by 2. 14 becomes 7, 22 becomes 11, 5 remains the same. Now our next number we're going to use is 5. So 5 divided by 125 equals 25. 7 remains the same, 11 remains the same, and the 5 becomes a 1. And one more time we're going to use 5. 25 becomes 5, 7, 11, and 1 remain the same. And once again we're going to count up our prime factorization numbers, which will yield us 1 to the first times 2 to the second times 5 to the third times 7 to the first times 11 to the first. And that is our final prime factorization expression. Now moving on to number 5, you see a set of gears here, a pair. One has 48 teeth, for the sake of the question. The larger one has 84. And the question that we need to solve is, at what point will these gears, the teeth that are currently touching, how many rotations will they make until the same gears are touching once more? Now, the graph does not exactly represent 48 and 84 teeth, respectively, but for the sake of the question, we'll make it work. So how many rotations will these gears have to make before the same teeth that are currently touching touch again? Now here, we're also going to be dealing with prime factorization. So, this time we're going to use our tree diagrams that we discussed earlier. So starting off with 48, we bring down into 2 and 24. Now 2 is a prime number, so we're going to leave that alone, and we're going to break down 24 further into 2 and 12. Once again, 2 is prime, so it stays. 12 gets broken down further into 2 and 6. And finally, the 6 will be broken down into 2 and 3. And now that none of these numbers can be broken down any further, we're going to take all of the prime factorization numbers and bring it over. So 48 will equal 2 to the 4th times 3. And now we're going to do the same thing with 84. We'll take the prime factorization of 84, which is 2 to 42, breaking down 42 to become 7 and 6, breaking down the 6 to become 2 and 3. And then we're going to take these numbers and do the same thing we did. That's supposed to say 84. We're going to do the same thing we did, which is 2 to the 2nd times 3 times 7. And then we're going to combine these two. Now you might think, oh, we're going to combine the exponents. Well, not entirely. The way this combination of prime factorization expressions work, or rather equation because of the equal sign, is the larger of the prime factorizations are going to swallow up the smaller one. So 2 to the 4th will swallow 2 to the 2nd. 3 and 7 will simply combine with the 2 to the 4th. And then the next step is going to be to write out the full answer of 2 to the 4th times 3 times 7. So 2 times 2 times 2 times 2 times 3 times 7 equals 336. And then the final step will be to take that final number, we're going to divide it by the number of teeth in the smaller gear, and finally that number will be 7. So these gears have to make 7 rotations before the same teeth that are touching currently will touch again. And now we are going to move on to our final question of the presentation. We're going to be dealing with a magic square. Now, what is a magic square? Well, I'm going to explain it to you. This square, as you can see, has 2 given numbers, 0 and 1. And the first goal we're going to discuss is finding the magic sum. What is the magic sum? Well, the magic sum is the sum number that all of the numbers that will eventually show up in this table will add up to become in every direction, vertically, horizontally, and diagonally. All the numbers in those paths will equal that sum total. And we're going to use x for the current moment to represent the magic sum number. So moving on, we have the numbers -7, -6, -5, -4, -3, -2, -1, 0, and 1. So you might be wondering where we go from here. Well, what we're going to do is, before we even start placing any numbers, we have to find the magic sum. So what we're going to do is we're going to add all of these numbers together, the negatives and the positives and the 0, and we're going to give a grand number total of -27. Now the next step in this operation is we're going to use the number 3, and we're going to multiply that by the magic sum x to equal -27. So from here, it's as simple as dividing -27 by 3. Now what times 3 equals -27? Well, if you said -9, you get a gold star because you're correct. So now that we have our magic sum, it's no longer x, it's -9. Now that we have our magic sum number, we have to place the numbers in a way that the horizontal, the vertical, and the diagonal all equal that sum number. So the numbers have to be placed in ways that all the directions will work. Now, there is no clear, easy method to get through this. It's a matter of trial and error. And trial and error is simply, it's like a hypothesis. You're going to continue to take guesses. You're going to continue to test your guesses. And if it doesn't work, you restart and try again until you've come to your grand answer, your final number placement, which I will show you here. -5, -4, -7, -2, -3, -1, and -6. Now, the trial and error method does take a certain amount of time. It is not easy, and it is by no means a foolproof method, because mistakes will happen. But so long as you keep a cool head and you keep track of all of the incorrect answers, you will eventually reach your final answer. And an easier way to subvert trial and error is to use different kinds of reasoning, such as deductive. Once you find a combination that works, you can then move on to other combinations, and if they continue to work, you'll eventually reach your final answer. And that would be the end of our presentation. Now, I hope I've explained this to you guys as best I can. I know I had a bit of a difficult time learning some of these. They're not exactly the easiest methods, so I don't blame you if you have to take some time. But with hard work, using your critical thinking skills, and if you're taking good notes, you should be able to understand these no problem, just as I did. That is all the time I have for tonight. I hope I helped you guys learn a bit more about these integers and different chapter questions, and I will see you guys on the next video presentation. So as always, you rock, and have a good night.